All right, this is Jack Jackson back again in our continuing look at different congruence criteria for triangles in various geometries. For this one, let's take a look at hyperbolic geometry and the SSS condition. Now recall that we were able to look at the SSS condition in Euclidean geometry, and we found that, what do we find? We found that if the triangle satisfied the triangle inequality, then there was one triangle possible. If not, there was no triangle possible. And if there was a triangle possible, then they all had to be in one congruence class. So if you had two triangles satisfying the SSS criteria, that is, all pairs of corresponding sides were congruent, then in fact the triangles we saw did have to be congruent. So this is the same thing here for hyperbolic geometry using the half-plane model, as I've been using in my videos. So here is a circle of a certain radius, and we can pick A to be any point we want in the plane. Now this circle is staying the same size as is measured in hyperbolic geometry. Remember, in some sense, the metric is sort of more dense along closer to the Euclidean, closer to the edge there. Okay, so there's a side that we fix. Now we use a compass and make a circle of centered at A of the radius B, and one at C of the the point C has to be on this circle. That circle is a distance right now of 2 from A. It also has to be a distance of 3 from B. That would place it on this circle down here. And there's actually two places that they meet. There's one of them right there. And we can complete the triangle with our hyperbolic line segments. Notice that these are the indicated lengths. Then we could measure the angles and see what they are. And it turns out that no matter what, say, for example, if we had chosen the other place where they meet, those two triangles are congruent. They're actually hyperbolic reflections of each other over this hyperbolic line containing A and B. So this angle, notice, see, it has the same measure as the angle down here. These two angles here have the same measure. These two angles here have the same measure. You can see them here and here. And of course, all the lengths were the same because of the way we set it up. So in fact, this works. We can modify the triangle a little bit. We can move B around to a different place. We have different triangles now, but both of these are in the same congruence class. They are congruent to each other. Even works if we have a vertical, well, might not be able to draw it, but it works with a vertical side too. Something just disappeared on me. Okay. But in any event, we get this to work out. Okay, so maybe a little bit buggy there on that, but I think you can see that the side condition is enough for hyperbolic geometry, exactly like it is for Euclidean geometry.